Imagine a metal so tough that a steel hammer would barely dent it, so dense that a small block of it would feel surprisingly heavy in your hand, and so heat resistant that it can glow like the sun without melting. That metal exists. It's called tungsten. Often hailed as nearly indestructible, tungsten is a chemical element that has fascinated scientists and engineers for centuries. In this video, we will explore what makes tungsten special, from its curious name and its discovery story to its remarkable physical and chemical properties, how we obtain it from the earth, and the many ways we use this super metal in everyday life. So welcome to Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, hype, subscribe, and hit the notification bell so you will never have to miss another episode. Also, make sure to fill in the poll in the post section of the channel for next week, as we will be doing another experimental deep dive again. Now, what we have here is by far the heaviest cube in the collection, and here is a scale to show what a normal cube, in this case of rubidium, would weigh. It's 148 grams. But this cube of tungsten is massive and weighs 354 grams. But the stuff inside here doesn't look that big. Now, we also recently started a collection of elements outside of cubes, thanks to Nova Elements, and here we have a few pieces of tungsten, and you can see they're also very heavy compared to other metals. And that brings us to the question, can you lick it? So, can you lick tungsten? Well, surprisingly, yes. If it's pure, solid tungsten metal, it's not dangerous at all. And the periodic licking table is also agreeing with us. Tungsten is extremely chemically inert, which means it doesn't react with water, saliva, or acids in your mouth. It won't dissolve, it won't poison you, and it won't give you that sharp metallic taste like copper or iron. Most people report no taste at all. What you will notice is that it will feel very cold because tungsten conducts heat very well and pulls warmth from your tongue faster than most materials. That said, it only applies to clean, solid tungsten. You absolutely should not lick tungsten powders, dust, oxides, or industrial forms like tungsten carbide tools, which often contain cobalt binders that are toxic. Fine tungsten dust is also dangerous to inhale. Not sure why I mentioned that, because this segment is not "Can you snort it?" Tungsten's story begins in the world of minerals and alchemy, long before it found its way into light bulbs and drill bits. In fact, over 350 years ago, Chinese artisans unknowingly used tungsten in a pigment to create a unique peach-colored glaze on porcelain. However, in the West, the element remained hidden within heavy black and yellow ores until the 18th century. European chemists first suspected this new metal around the 1770s. In 1779, an Irish-born mineralogist, Peter Wolff, examined a heavy mineral from Sweden, now called scheelite, and concluded it likely contained a previously unknown substance. He couldn't isolate the metal, but his hunch set the stage for further discoveries. A few years later, in 1781, the renowned Swedish chemist Carl Wilhelm Scheele got hold of a dense mineral from an iron mine nicknamed tungsten, or heavy stone, by local miners. From this ore, Scheele managed to extract a strange yellow acid, later named tungstic acid. He rightly suspected that if this acid could be reduced, essentially having its oxygen stripped away, it would yield a new metal. Scheele didn't have the chance to perform the reduction himself, but he published his findings, sparking the interest of other scientists. The breakthrough came in 1783 in Spain at the Basque town of Vergara. Two Spanish brothers and chemists, Juan José and Fausto Eluar, were intrigued by Scheele's work. They investigated a different heavy mineral, wolframite, which miners had long cursed for complicating tin extraction. The Eluar brothers discovered that wolframite contained the same mysterious acid Scheele had found in scheelite. By heating this mineral acid with charcoal, carbon, in their laboratory furnace, they successfully reduced it to a metal, the new element at last. Now, they had isolated tungsten, though the brothers actually called it wolfram at the time. Credit for discovering tungsten is given to the Eluars in 1783, marking the first time this metal was obtained in pure form. In 1847, an English chemist named Robert Oxland patented methods to produce tungsten chemicals and even tungsten metal, which finally made larger quantities available. By the mid-19th century, metallurgists were experimenting with tungsten in steel alloys. In 1857, Oxland described iron-tungsten alloys, planting the seed for what would later become high-speed steel, a tungsten-containing steel vital for cutting tools. Still, the pure metal itself found no major applications throughout the 1800s. It was simply too hard to shape and too rare to use it widely. All that changed at the dawn of the 20th century. The age of the electricity brought a sudden demand for metal that could withstand intense heat. Early electric light bulbs used carbon filaments that burned out quickly. Inventors around the world were searching for a better filament material that could glow white hot without melting or evaporating. Tungsten was a prime candidate. It had the highest melting point of any metal, meaning it could run hotter and brighter than carbon. The challenge was drawing tungsten into a fine wire, since tungsten is notoriously brittle in bulk form. In 1908, American metallurgist William D. Coolidge at General Electric developed a special process to make ductile tungsten wire. He poured tungsten oxide, reduced it to a metal powder, pressed it sintered into a rod, and then carefully forged and drew it at high temperature. The result was a thin, flexible filament of tungsten. By 1910, tungsten filaments began to replace carbon in light bulbs, lasting longer and shining brighter. By 1911, tungsten filament bulbs were widespread, revolutionizing lighting. Tungsten finally had a starring role in industry. Tungsten's value grew immensely, and interestingly, it became the focus of a patent battle. General Electric tried to assert a patent monopoly on tungsten filament production based on the Coolidge method. But in 1928, the US court struck down GE's claim, famously ruling that you can't patent a natural occurring element. This made tungsten one of the only chemical elements to figure in a major patent lawsuit, a testament to how important tungsten had become for modern technology. The metal's importance extended well beyond light bulbs. By World War I, 1914 to 1918, tungsten had emerged as a strategic military resource. Its exceptional hardness and heat resistance made it ideal for strengthening steel armor and for making better cutting tools in munition factories. Tungsten carbide tool bits, for example, could machine tough steel for guns and engines more effectively. Recognizing this, nations scrambled to secure tungsten supplies. Britain in World War I took steps to control tungsten mines like the Carrockfell mine in England to deny access to the German military. During World War II, tungsten played an even more dramatic role. At the time, Portugal had the largest deposit of wolframite, tungsten ore, and was one of the main sources of tungsten in Europe. Both Axis and Allied powers desperately wanted this nearly indestructible metal for their war industries, especially for armor-piercing shells and cutting tools to manufacture weapons. A sort of tungsten tug-of-war ensued in the background of World War II, sometimes called the Wolfram Crisis. Portugal, while neutral, was pressured and bargained with by both sides for its tungsten ore. After the World Wars, tungsten continued to be crucial in the Cold War era and beyond, albeit in a different way. Industries in the later 20th centuries adopted tungsten for peacetime innovations. Aerospace engineers used it in rocket engine nozzles and turbine blades. Car makers and miners relied on tungsten tools, and scientists found uses for tungsten in electronics and even in medical devices. Tungsten was no longer a rare curiosity. It became a foundation of modern technology. Now, tungsten's name carries a little bit of history and folklore. The word tungsten comes from Swedish, and it literally means heavy stone. Swedish miners long ago used tungsten as the name for a dense mineral now known as scheelite, calcium tungstate. Scheelite, which is an important ore of tungsten, is indeed very heavy for a rock, so the old name heavy stone fit well. When the new metal was isolated from this heavy stone, the name tungsten naturally carried over to its element, at least in English and Swedish. and many other languages too. But tungsten has a second name that you'll encounter, especially in other parts of the world: wolfram. This is why tungsten's chemical symbol is a W, not T or Tu, but W for wolfram. The term wolfram comes from German, and it has an interesting origin in medieval mining folklore. The most common tungsten ore, wolframite, often occurs mixed with tin or cassiterite in the same deposits. Old miners noticed that when smelting tin, if wolframite was present, the yields of tin would be much lower. It was as if some greedy creatures was devouring the tin. So they nicknamed that troublesome mineral wolfram or wolf's foam, also wolf's spittle in some accounts, suggesting that a wolfish spirit in the ore was eating up the tin like a wolf devours its prey, leaving a frothy residue. The name wolfram stuck for the mineral and eventually for the metal extracted from it. So we have two names: tungsten, heavystone, and wolfram, wolf devourer. In 1783, the Ulhuar brothers, who first isolated the element, used the name wolfram. And many countries, especially in Europe, also the Netherlands, we call it wolfram, continued calling it wolfram ever since. For example, in Germany, Spain, and Russia, the element is commonly referred to as wolfram, whereas English, French, and Scandinavian languages use tungsten. The dual naming persisted through the 19th century until international scientific conventions settled on W as the symbol, honoring wolfram, and tungsten as the English common name. So why do we call tungsten nearly indestructible? Well, the answer lies in its extraordinary physical and chemical properties. Tungsten holds several world records in the realm of materials. First and foremost, it has the highest melting point of all metals. Pure tungsten doesn't melt until heated around 3420 degrees Celsius. That's about 6192 degrees Fahrenheit. Now, to put that into perspective, the temperature is comparable to the surface of the sun and far above the melting point of iron, 1538 degrees Celsius, or titanium, 1668 degrees Celsius. In fact, of all the elements, only carbon has a higher heat tolerance. Carbon doesn't melt, but sublimes around 3700 degrees Celsius. Now, what that means in practical terms is that tungsten can take heat that would liquefy other metals. If you held a tungsten filament in a flame of a blowtorch, it would glow white, hot, and yet remain solid. This astonishing heat resistance is one reason tungsten is so valuable for light bulb filaments, rocket engine parts, and any other applications involving high temperatures. Now, tungsten, as we've seen, is also incredibly dense and heavy. It has a density of about 19.3 grams per cubic centimeter, very close to that of gold. In fact, tungsten is roughly 1.7 times heavier than lead. Imagine holding two metal cubes of the same size, one lead and one tungsten. The tungsten one would noticeably outweigh the other despite identical dimensions. It's amusing to note that tungsten's heft and nearly gold-like weight have even led to some dubious uses. For example, criminals gold-plating tungsten bars to pass them off as pure gold, since by weight they are eerily convincing, all thanks to tungsten's high density. Another standout property of tungsten is its hardness. On its own, pure tungsten metal is very hard, harder than many types of steel. In fact, a purified tungsten rod can scratch glass with ease. However, in its common form as a sintered polycrystalline metal, tungsten can be somewhat brittle at room temperature. Now, if you try to bend or hammer a typical tungsten bar, it might crack or shatter rather than deform. This brittleness is because of tungsten's rigid crystalline lattice and the presence of impurities or grain boundaries. Interestingly, if tungsten is ultra purified and made into a single crystal form, it becomes more malleable, able to be bent, while still retaining hardness. Engineers have found that working tungsten at high temperatures or adding small amounts of other metals can improve its toughness. For example, tungsten wire for light bulbs is doped with tiny amounts of potassium and other elements to prevent it from becoming brittle and to keep the filament from sagging when hot. Tungsten also boasts the highest tensile strength of any metal at temperatures above 1000 degrees Celsius. While many metals soften as they get red hot, tungsten stays strong. It also has the lowest thermal expansion coefficient of any pure metal, meaning it hardly expands or contracts with heat compared to others. Now, this stability is important for applications like high-precision machine parts and glass-to-metal seals. Tungsten's expansion rate closely matches that of borosilicate glass, making it useful to fuse metal and glass together without cracking. Chemically, tungsten is remarkably resistant to attack. If you expose most metals to water or air, they'll corrode or tarnish over time. Iron rust, copper patinas, etc. Tungsten, in contrast, does not react with oxygen at room temperature. It effectively doesn't rust or oxidize in normal conditions. You can leave a piece of tungsten metal out and it will remain shiny gray indefinitely. It's also impervious to water and most acids. Neither hydrochloric acid, nor sulfuric acid, nor even aqua regia, a mix of nitric and hydrochloric acid that dissolves gold, will easily eat through tungsten. Only a couple of aggressive mixtures can corrode it. A hot concoction of nitric acid and hydrofluoric acid can slowly attack tungsten, and molten alkali chemicals can too. But in everyday terms, tungsten is chemically stable and inert against almost everything. This inertness is one more reason it's considered indestructible. It doesn't readily burn, corrode, or dissolve. Now, when tungsten does form compounds, it shows off its multi-talented chemistry. Tungsten can exist in a variety of oxidation states from -2 to +6, but the most common is +6. The oxide tungsten trioxide, WO3, not World War III, is a stable yellow compound that forms when tungsten metal is heated in air to high temperatures. Tungsten can also combine with carbon to form tungsten carbide, WC, which in Dutch means toilet. One of the hardest substances known. We'll talk more about this under uses. Tungsten carbide's hardness is about 9.5 on the Mohs hardness scale, nearly approaching diamond's hardness of 10. Tungsten forms many other compounds as well, with chlorine, sulfur, and so on. But its carbides and oxides are especially noteworthy for their robustness. Now, tungsten may be a superstar in the metal industry, but it's actually quite scarce in the Earth's crust. It's not as rare as gold or platinum, but it is far from abundant. Geologists estimate that tungsten makes up only about 1.5 parts per million of the Earth's crust, roughly 1.5 grams of tungsten per ton of rock. For comparison, that's on par with elements like tin or molybdenum. The primary ores for tungsten are two minerals we've already met, wolframite and scheelite. Wolframite is a blend of iron and manganese tungstate. Chemical formula looks like this. It's a heavy brownish black mineral that was the bane of tin miners in old times. Scheelite is a calcium tungstate, typically found as dense pale-colored crystals that can even fluorescence under UV light. Both of those minerals have a high tungsten content and are the main source of tungsten in mining. Other tungsten-bearing minerals exist, like stolzite and ferberite, but they are much rarer or not economically significant. Tungsten mining usually happens in hard rock mines, often in mountainous regions. Historically significant tungsten deposits were mined in countries like Spain, Portugal, Germany, in the Ore Mountains, and Bolivia. In the modern era, the vast majority of the world's tungsten comes from China. China has extensive tungsten ore reserves, and by some estimates produces around 80% of the world's tungsten supply today. Other notable producers include Vietnam, Russia, and Bolivia, and smaller amounts come from countries like Rwanda, Austria, scheelite mines in the Alps, and United States, which has some reserves but limited current production. Once tungsten ore is mined, pulled out of the ground as wolframite, scheelite, etc., how do we get it to usable metal? Well, the production of tungsten metal from ore is a multi-step process that is quite chemistry intensive. The raw ore is crushed and then concentrated to increase tungsten content. Because tungsten ores are heavy, methods like gravity separation, shaking tables, spirals, and magnets separation are used to separate wolframite or scheelite from lighter waste rock. The result is a tungsten-rich concentrate, often containing 60 to 70% of tungsten oxide content. The concentrated ore is then chemically processed to convert into pure tungsten oxide. One common method is to digest the concentrate in an alkaline solution. For example, scheelite can be decomposed by boiling it in sodium hydroxide solution, which dissolves the tungsten into a sodium tungstate solution. Wolframite concentrate might be fused with sodium carbonate. In either case, the goal is to get a soluble tungstate compound. The solution is then acidified, causing tungsten acid or hydrated tungsten oxide to precipitate out. This precipitate is filtered and roasted to yield pure tungsten trioxide, a fine yellow powder. So now we have tungsten in oxide form and we need to reduce it to metallic tungsten. This is typically done by reduction with hydrogen gas in a high temperature furnace. The tungsten trioxide powder is heated in a stream of hydrogen, which chemically strips away the oxygen. Now the reaction looks something like this, and the end product is powdered tungsten metal and water vapor that escapes. Sometimes carbon, coke, is used as a reducing agent instead, though hydrogen is cleaner and yields higher purity metal. The tungsten at this stage is a gray powder, not very useful as a structural material because tungsten's melting point is so absurdly high, casting molten tungsten into ingots or shapes is impractical. You need special furnaces well above 3400 degrees Celsius, which are expensive and energy intensive. Instead, industry usually resorts to powder metallurgy techniques. The tungsten powder is blended with a tiny bit of binding material, often nickel or iron powders, pressed into the desired shape and then sintered, heated below melting point, to fuse the particles together. Now, during sintering, the small additive nickel iron diffuses and helps bind tungsten grains, resulting in a solid piece. This is how dense tungsten parts like rocks, blocks, or spheres are made. Now, for producing tungsten wire for lamps or electronics, the sinter tungsten rod is swagged and then drawn through dies at high temperature to stretch it into a thin wire. A challenging process, but one mastered over a century ago for light bulb production. Now, because of its special properties, tungsten has found its way into an amazing variety of applications. Let's explore how we use tungsten in the modern world, from industry to household items, often taking advantage of that near indestructibility. One of the biggest uses of tungsten is in the form of tungsten carbide, a compound of tungsten and carbon. Tungsten carbide is an ultra-hard material, about as hard as diamond, and it revolutionized cutting tools. If you ever had a dentist drill on your teeth, there's a good chance the drill bit had a tungsten carbide tip. Likewise, the blades and drill bits that cut through metal in factories, the mining tools that crush through rock, and the heavy-duty abrasives used to grind and polish all often contain tungsten carbide. Now, these tools can cut other steel tools without dulling. Thanks to tungsten to make tungsten carbide, tungsten powder is mixed with carbon and heated to a high temperature. Then usually cobalt metal is added as a binder to form a very hard cemented carbide composite. The result is a material that can hold a sharp edge and endure friction and heat that would destroy ordinary steel. Approximately half of all tungsten mined is used to make these hard carbides. It's a cornerstone of the metalworking, mining, and construction industries. Whenever you hear the term carbide tipped blade or bit, that's tungsten at work, chewing through tough materials with ease. Tungsten's claim to fame in the public eye is surely the incandescent light bulb filament. For over 100 years, tungsten wires inside bulbs have illuminated the world. When electricity passes through the thin tungsten filament, it heats up to around 2500 to 2700 degrees Celsius and glows bright yellow-white, emitting light. Now, tungsten can survive this heat without melting since its melting point is much higher, and it resists evaporation enough to last hundreds of hours. Even though many countries are phasing out the old incandescent bulbs in favor of LEDs or fluorescents for efficiency reasons, tungsten filaments are still used in certain lamps like halogen lamps and some specialty bulbs. Beyond lighting, tungsten's heat resilience makes it ideal for heating elements in high-temperature furnaces and for arc welding electrodes. In TIG welding, tungsten inert gas welding, a tungsten electrode is used to generate an electric arc that melts other metals, and the tungsten electrode uniquely does not melt itself in the process. Similarly, in vacuum tubes and electron microscopes, tungsten filaments can serve as cathodes, electron emitters, because they can get white hot and emit electrons for long periods without burning out. Tungsten is often added in smaller quantities to other metals to create strong alloys. Prime example is high-speed steel, an alloy steel that can cut at high temperatures. High-speed tools might contain around 5 to 18% tungsten, along with other elements like chromium and vanadium. The tungsten boosts the hardness and hot strength, allowing drill bits or lathe cutters made of high-speed steel to stay sharp even when they get red hot from friction. Tungsten is also used in superalloys, specialized alloys for jet engines, turbines, and other extreme environments. Alloys like Hastelloy and Stellite include tungsten to improve their high-temperature performance and wear resistance. In the aerospace industry, tungsten alloy parts have been used in rocket engine nozzle throats and the leading edges of re-entry vehicles, parts that must withstand blistering heat during atmospheric entry. The metal's ability to stay solid and strong under such conditions is invaluable. Tungsten's density and hardness make it the go-to material for military hardware. For example, armor-penetrating ammunition often uses cores made of tungsten-heavy alloy. A spear-like dart of tungsten, fired from a tank or an anti-tank weapon, can punch through armored vehicles with kinetic energy, essentially using tungsten's weight and strength to pierce through steel armor. Tungsten alloys, usually tungsten mixed with nickel and iron or cobalt, are used to make kinetic energy penetrators as an alternative to depleted uranium shells. Unlike uranium, tungsten isn't radioactive or pyrophoric, so it's a cleaner option. Though just as dense, military history saw tungsten-tipped shells employed in World War II, and they continue to be important in modern armor-piercing rounds. Tungsten is also used in shrapnel for advanced munitions. Some modern grenades and missiles use tungsten powder to create high-density, short-range shrapnel that is extremely destructive to a target but loses momentum quickly, reducing collateral damage farther away. Another defense use is in shielding. Tungsten's density helps to block radiation, so it can serve as a shielding in portable X-ray units or containers for radioactive material where lead might be too bulky or soft. All these uses rely on tungsten's status as one of the hardest, heaviest, non-toxic metals available. Now, one of the most extreme uses of tungsten is in armor-piercing, fin-stabilized discarding sabot, usually shortened to APFSDS, and honestly, I wouldn't have known this until somebody put it in the comments last week. This is the kind of ammunition used by modern tanks when they need to punch through heavily armored targets. Instead of relying on explosives, these rounds use pure physics. The core of a projectile is a long, thin rod made from extremely dense material, often tungsten-heavy alloy. The idea is simple. Concentrate as much mass as possible into the smallest area and then throw it at an unbelievable speed. Now, the sabot part is a lightweight shell that surrounds the tungsten rod while it's inside the tank barrel. This allows the rod to be fired from a much wider barrel than the rod itself. Now, once the round leaves the barrel, the sabot peels away and falls off, leaving the tungsten penetrator flying on its own. Small fins at the back stabilize it in flight, like the feathers of an arrow. By the time it reaches its target, the rod is traveling at several kilometers per second, fast enough that armor doesn't do much to block. Now, tungsten is ideal for this role because it combines extreme density with incredible strength. When the rod hits armor, the sheer kinetic energy causes the steel to behave almost like a fluid. Now, whenever something needs to be heavy and compact, tungsten is a great solution. It's used as counterweight and ballast in various vehicles and equipment. For instance, in race cars like Formula 1 and NASCAR, tungsten blocks are used as ballast to fine-tune weight distribution because you can pick a lot of weight in a small space, freeing up more room in the car design. In airplanes and yachts, tungsten ballast can stabilize the craft with less volume than traditionally lead weights. Even the Mars rover mission in 2012 employed tungsten. The entry vehicle of NASA's Curiosity rover had tungsten weight that were jettisoned to shift its center of mass for precise atmospheric entry. Competitive golfers have tungsten inserts in clubs to adjust the balance, and some high-end tennis rackets use tungsten in weights too. Even firearm enthusiasts use aftermarket tungsten guide rods or weights in guns to reduce recoil due to the extra mass. Surprisingly, tungsten has made its way into jewelry as well. Tungsten carbide rings have become popular in recent years for wedding bands and fashion rings. They have a steely gray shine, which can also be plated to appear gold or black, and they are extremely scratch resistant. A tungsten carbide ring will not easily get scuffed or worn, keeping a polished look for a long time. This appeals to people who want a ring that stands up to daily wear and tear. Tungsten's contributions to technology are numerous. In electronics, tungsten is used inside integrated circuits. Tiny tungsten vias and interconnects connect transistors in many microchips. Tungsten can be deposited in thin films for wiring that withstand the heat of a chip fabrication and does not diffuse into silicon easily. The semiconductor industry has long used tungsten in the back-end metallization of chips for things like contacts and plugs because it has good conductivity and a high melting point, so it doesn't melt during chip operation or fabrication steps. Tungsten is also a metal of choice for targets in X-ray tubes. If you've ever had an X-ray at the dentist or hospital, the X-rays were likely generated when high-energy electrons hit a spinning tungsten disk, the anode. Tungsten's high atomic number and heat tolerance make it ideal for this. It produces a lot of X-ray photons when struck by electrons, and it can endure an intense heat from the electron beam. Similarly, tungsten shields and collimators are used to shape and block radiation in medical imaging and radiation therapy equipment. Another everyday device that benefits from tungsten is the smartphone. A little vibration motor that makes your phone buzz typically uses a tiny eccentric weight, and often that weight is made of tungsten. The motor spins heavy off-center mass. Using tungsten allows that mass to be small yet weighty, giving a strong vibration without taking much space in your slim phone. So why is this metal nearly indestructible? Because nature endowed tungsten with the ability to endure extremes. It laughs at high temperatures, shrugs off corrosion, and wears its heavy metal crown with pride. When we harness tungsten, we're effectively borrowing one of nature's toughest tools for our own needs. Tungsten is a brilliant example of how an element can be both fundamentally useful and profoundly inspiring. It reminds us that the periodic table holds some remarkable characters. In tungsten's case, one that is heavy, resilient, and unyielding. Now, we would like to thank the members that support our channel. Thanks for doing that. We really appreciate you. Now, if you think we missed anything, tell us in the comments. And if you want to know more about another dense element, take a look at this old video about osmium next.